Okay, welcome to the session of econometrics. I'm not Andrew Chesher. I'm Jianqing Fan, Frederick Professor of Finance and Professor of Statistics at Princeton University. So I'm the chairman of this section, so I divided time, so we have about 80 minutes or 40 minutes each. So give maybe about 35 minutes and then 5 minutes, around 5 minutes for a question. So, excuse me. The first speaker is Andrew Chesher of University College London. So he is William Stanley Jevon Professor of Economics and Econometric Measurements. He's a director of ESRC Center of Macro Data Methods and Practice. He's fellow of British Academy, Econometric Society, and honorary member of American Economic Association. So he has made many wonderful contributions to econometric theory, methods, and practice, and to macroeconomic methods and identification analysis. So let me not take in more of your time. So let's welcome Andrew.
Well, thank you for those kind remarks, and thank to the Society and to the organisers for giving me the opportunity to speak today and the opportunity to attend this very stimulating meeting. So the research I'm going to talk about today is joint work with my colleague Adam Rosen at UCL and CMAP, and the purpose of this research is to extend the application of instrumental variable models to situations in which they have not so far been applied. So what I mean by an instrumental variable model for the discussion today is a model which is firstly incomplete. The classical single equation model in which we have some endogenous outcome on the left-hand side of a structural equation, and on the right-hand side some endogenous variables determined by the process we're observing, but for which there is no specification of the way in which those endogenous variables are determined. It is as if there were a simultaneous equation system delivering one or more solutions, and only one of the equations has been specified by the econometric researcher. And the other aspects of these models that gives them their name, I guess, is that there are some instrumental variables, and we are prepared to state that there is some restriction on the dependence of those the joint dependence of those instrumental variables and the unobservables that are pushing the process along through time. Here are some examples. We go back to the dawn of econometric time, the linear model studied by Koopmans, Rubin, and Leibniz. If you read this Coles monograph 10 paper, you'll see, or just as soon as they've dealt with the identification of the parameters of a fully specified system of equations, they immediately move on to consider what could be known if you were only prepared to specify one of the equations. And Koopmans, I'm told by Peter Phillips, set Ted Anderson homework one day, which was to figure out how to do efficient estimation in that context, and the Limmel estimator came out. Tile produced two-stage least squares as a way of estimating this sort of model. There's been a lot of developments since, some milestones, the additive unobservable non-parametric model of Newey and Powell, and much more, and more recently, the non-additive unobservable error model of Chernozhukov and Hansen and the other authors there. Notice that on the right-hand side of all these equations is some endogenous variable that's not restricted to be independent of the unobservable u. U is unobservable throughout today. And there is, though, some restriction on dependence between u and these exogenous variables, by which I mean variables not determined by the process, z1 and z2. Notice a feature of these models is that this unobservable is always in these models a scalar object. It's not multidimensional. All of human variation is captured through variation in a single scalar random variable that lives on the real line. And there's also a continuity. If u is continuous, then y1 is continuous. And strict monotonicity in this function g in this last case gives us that result. No scope here for discrete variation in y1 if u is continuous with this strict monotonicity restriction, certainly not in these additive models. No scope for human variation to exist in more than one dimension. Rather remarkable, given the choices I see people making at breakfast under apparently similar circumstances. So these incomplete IV models are commonly applied when there are therefore continuous outcomes and a single scalar source of heterogeneity, but they aren't applied, we find, when outcomes are discrete or when heterogeneity is multidimensional. And the new direction in the title of this talk, New Directions for IV, describes the extension of the scope of incomplete IV modeling to situations in which there is discreteness and or there is high-dimensional, more than one-dimensional heterogeneity capturing the variation in human behavior. An example of a model in which we naturally have multidimensional unobservables would be McFadden's discrete choice model from the 70s, where there's an unobservable associated with each of the alternatives that you face, and a single scalar outcome which is discrete, which indicates which of a number of mutually exclusive alternatives is chosen. If this works, then we will be able to deal with endogeneity in ways we haven't done before in a whole variety of cases: probit, logit, tobit models, nested logit models, ordered outcome models, multiple discrete choice, models of sensor durations and counts, models of random coefficients, stochastic factor models, all of these things with endogeneity. And actually the methods that we're talking about apply more generally to, for example, auction models is a good example. But why bother with all this? We've got perfectly good point identifying models for these discrete outcomes, and with high dimensional heterogeneity, we could just build a complete model, for example, or we could invoke some conditional independence assumption which says that as long as we can observe some appropriate objects, then endogeneity vanishes if these objects are held fixed. All the endogeneity between y2 and u in those circumstances will be due to the common variation of an underlying cause, which fortuitously on the day is something that can be measured. Well, why bother? What's so great about incomplete models? I guess it's the answer that was provided back in the 50s and the 40s by the founders. What incomplete models let us do, they're very suitable. Economic process is very complicated. It's not a ball rolling down an inclined plane and we're trying to figure out how the slope affects the speed, which it travels. Very, very complicated. And what incomplete models let us do is they focus on just the main elements of that complex process that are of interest from some policy point of view. What is the returns to schooling? I don't care about how schooling was determined necessarily when I want to answer that question for a policymaker. They allow us to economize on modeling effort because they require less knowledge of the process. I could tolerably well model the demand for fish and figure out what would happen if the price of fish went out without necessarily having to decide on what are the fisherman's choices of how much to go catch and under what conditions. Though my instrumental variable there might be weather conditions, so I would have to believe that when weather is bad, he doesn't do such a good job as when weather is good. And the third thing is that these incomplete models are potentially robust to misspecification of the part that has to be filled in if we construct a complete model. Now what we do is we show in this research, which has gone through a sort of number of stages and a number of papers, and we've slowly learned a bit more about the problem as it's proceeded. What we show is that these incomplete instrumental variable models are generically partially identifying when outcomes are discrete or when there are multiple sources of heterogeneity. Actually, the key reason why this happens, the deep reason why this happens, is that in all of these cases, the unobservables cannot be expressed as single-valued functions of observables. So with the discrete outcome, there's typically a range of the continuous underlying unobservable that gives rise to a particular discrete value. And with random coefficients, there's typically a manifold upon which these random coefficients that can lie, that can deliver a particular value of the endogenous outcomes for given values of the exogenous variables. And when you look at the theory that we work with, you'll see that it's this combination of having a set-valued residual on the one hand and the incomplete model delivering not a singleton value for the endogenous variables. It's this combination which leads to this general partial identification result. We characterize sharp identified sets of structural features at quite a high level of generality and then specialize down to particular cases. What I'm going to do today is just set out the main elements of this research, as I say, done jointly with Adam Rosen, and illustrate using a model with an interval-censored endogenous variable. I use this because, firstly, it's in the paper, which I think should be available through the conference website, certainly available at our website at CMAP in London. And it's also an example that really shows these sets of y values and sets of u values very, very clearly. And what this does actually is to extend the results of Mansky and Tamer's Econometrica 2002 paper, in which they had an interval-censored explanatory variable, but that explanatory variable was exogenous. And what could you know of the coefficient on that explanatory variable if you only saw it falling in intervals? This is the illustration then that I'm going to use. There's going to be a linear model for an outcome y1, a scalar outcome y1, with an interval-censored endogenous variable y2 star. y1 is going to be, in the particular case I'm going to talk about, a linear function of endogenous y2 star, an exogenous z1, which may be a vector. y2 star is going to be scalar. There's an additive unobservable. But we don't observe y2 star. We'll just observe two random variables realizations, y2l for lower and u for upper. And what we will know, the model will say, is the probability that y2 star lies between these two variables is equal to 1. We'll observe y1, y2l, y2u, and z will be z1, z1, excuse me, I don't know whether I'm in America or England when I'm talking about this. And z2 will be some excluded variable, which may not be present, and if it isn't present, we aren't going to get very far with any identification, of course. If y2l was always equal to y2u, this would be, under many more conditions, a point identifying model. If z2 was there and did vary and moved y2 star around, z2 being binary would be enough. But to do this, I'm going to actually deal with an independence restriction and presume that u is independent of z. But no equation for y2 star, so it's an incomplete model. Nothing to say how y2l and y2u are generated either. It's completely left free. And of course, the identified sets that we're going to get out could be reduced if we were prepared to say more. Indeed, anything that is a special case of this is going to deliver a set or a point within the sets that I'm going to show to you. So there's going to be some interest here in figuring out what you could know with minimal restrictions. The implications for y1 of this are as follows. I'm going to suppose, as was, oh, that's very interesting. I'm going to suppose, oh, I see what happens here. Okay. It's like faulty connector. Speaker walked into computer. Cable came out. I'm going to suppose that beta is positive for this discussion. You could actually work through with beta negative, and data could tell you whether it's positive or negative. It'll be simpler if I just go with the restriction that beta is a positive quantity here, the coefficient on the endogenous variable. And then if we think about applying the right-hand side to y2l, y2 star, and y2u, you see that you must, with beta positive, get this inequality that appears here. This one here. But then what appears in the center is precisely y1. And so the implications of this model are that y1, y2l, and y2u must, for every u and z, satisfy this two-sided inequality. y1 lies in this closed interval. And the implications for u then, since we have this inequality for y1, are that u, the unobservable, lies in a set of values, and if you knew the value of y1, y2u, y2l, and z, you could know this interval for any particular values of the parameters. And the crucial question here is how on earth are we, if we only know that u lies in some set, and it's not a singleton, normally y is x beta plus u, and u is y minus x beta. If all we know is that u lies in a set, how are we going to exploit this independence restriction that u is independent of z? And that's the trick that we're going to pull. And unfortunately, in the time available, I don't have I don't have much time to go through the details, but I'll tell you the main results and perhaps give you a little bit of intuition. In general, these incomplete models with discrete or censored outcomes or non-scalar heterogeneity are going to deliver sets of values of outcomes, as you can see here. You tell me U, you tell me Z, you tell me beta and gamma. There's a set of values of Y1, Y2U, and Y2L that will satisfy that inequality. We can't pin it down without more completion of the model. And they're going to have set-valued residuals, as we call them. That U is going to live in some set that we could know if we knew the values of the Y's and the Z's and we knew the values of the parameters. So in order to deal with this, in our papers, what we do is to employ a construction as follows. We talk about models restricting a structural function, which I'll call H. In this case, that an example, it's characterized by coefficients beta and gamma, but in general it could be non-parametrically specified. H takes us from the support of Y, Z, and U to the real line, and it delivers closed level sets, which we've really just been looking at. So Y, script Y for a set of U, Z for a function H, is a set of values of Y that deliver a zero value of this function, and script U of Y, Z, and H is the set of values of U that deliver a zero value of this function at a particular value of Y and Z. And these are level sets of the same functions, and they are dual to each other in a rather deep sense, which is going to be used in our theoretical development. In the interval-censored endogenous explanatory variable case, with H, as I say, characterized by beta and gamma, the Y-level sets are just the sets of, for any U, Z, and for any H, i.e. beta and gamma values. These Y-level sets are just the sets of values of Y that satisfy this pair of inequalities. And the U-level sets are the sets of values of U that satisfy these inequalities. Okay, and we can write down a structural function that will deliver these as level sets, but it's in the paper, there's no point in writing it down now. Well, models in this setup are going to restrict this structural function. They're going to say it is linear or it has various features as it has in the example I've been dealing with. And it's also, the models are going to restrict probability distributions of the unobservables conditional on the exogenous variables. I'm going to use this script G notation to indicate the family of conditional distributions of U given Z. And there's one member of that family for every point in the support of Z. So if Z was binary, there'll just be 2, and otherwise more. Maybe an uncountable number of things in here. And as a notation, if I take G of U given Z and apply it to a set S, this delivers the probability mass placed by that probability law on that set. Okay. Data's going to, what models are going to do is to define which structures. So a structure is a pair, H coupled with a family of Gs. Models are going to define which pairs are admissible. All the H's that are linear, just like I had, coupled with all the G distributions that are independent of Z, and maybe also normal if I want to put in more restrictions. Data is going to inform about distributions of observable variables. Again, there's a family of these objects. I'm going to see Y, I'm going to see Z, and again, I'm going to use this notation for Fy of Z given Z applied to a set T is going to give me the probability mass placed on that set by this probability law when Z is equal to some particular value in its support. And the model's identified set, which I'm about to characterize in 2 slides, just give you the result, is the collection of pairs of structures that firstly are admitted by the model, have linear functions, have U independent of Z, U normal, whatever it is, and secondly, can deliver the distributions that we observe. Now, can deliver has got a slight kind of, we say a weasel word. One needs to say a great deal more about this, but I'm not going to say it today, and it's in the paper. Suffice to say that in order to do that, we would have to start to go into some different mathematics than we normally deal with, the mathematics of random sets, and I don't want to go into it now. But we can, I think, get an intuition on what's going on in the following way. So think about these U-level sets. These are, for any particular values, think of beta and gamma in this example. These are the values of U that the structural function H says can deliver a particular value of the endogenous variables Y when the exogenous variables take some particular value Z. For example, in this interval-censored endogenous variable case, where H is characterized by a pair of parameters, because it's a parametric model, U of y, z, and H is a closed interval on the real line. And you give me a realization of y1, y2u, y2l, and z, I can pin that down as a particular interval for any particular value of beta and gamma that you give to me. I can go calculate it. Okay. So recall these levels, and what I'm going to do now is to define two particular sets of values of u, of two particular sets of values of y, and then give you the main result from our paper, and then show how it works in this particular case. So let's consider a set of values of the unobservable. In this example, remember, the unobservable u lives on the real line. So we'll consider some particular interval on the real line. And for some particular function h, say a parameter, beta and gamma, let's define two different sets of values of y. Here's the first one. I'm going to call it script j. It's going to depend on the set of values of u that I choose. It's going to depend on the value of the exogenous variable z. It's going to depend on the structural function h. And what this is, it's the values of y which the structural function h says can occur if u lives on this set S and cannot occur when it doesn't. It's as simple as that. These are the things that can occur only if u takes values in this set. And in sort of set theoretic notation, this is the set of values of y such that this u level set is entirely contained in the set S. Okay? So if u's entirely, u values that live in there, this delivers values of y that can only happen if u lives in the set S, and it can't happen otherwise because there's no intersection of this u set with values outside the set S. And then we think of another a set of values of y. These are the values of y which the function h says can occur if u lives in S, so it's got all the guys in there I've already seen, and may occur if u's not in S. But excluded from this are the values of y that can only occur if u isn't in S. They're excluded from this set K. There's two sets. One's a subset of the other. The J set's a subset of the K set. Right? Maybe equal to it. Actually, if u is a singleton, which will be the classical case, they'll be equal to each other. Because a singleton's either in or it's out. Can't be in and out of a set. And that's actually the special case. As a special case of what we do, we will get all the classical results out as a bunch of equalities. Because what we're going to get from this is the following. This theorem, so here's just a reminder of what these sets are. And this is a CMAP working paper, January 2014. It's actually a revision of one that came out in the middle of last year. It tells us the identified set delivered by a particular bunch of distributions I observe, and a particular model comprises the structures that are emitted by the model and that satisfy this inequality, which I'll talk about in a second, for almost every value of z, and for all sets of values of the unobservable in some collection of closed sets on the support of the unobservable. And so what we have in the middle here is the probability mass the distribution of u given z puts on a set S. And what we have on the right is the probability of these values of y occurring, something we can see in the data, because we've got information about f of y given z. This is the probability that values of y occur that can only occur if u lives in S. And it's kind of almost blindingly obvious that that inequality, the right-hand one, has to happen. If the things, the y's on the right can only happen when u lives in S, it's got to be the probability mass put on that's at least equal to the probability these particular y's occur. And on the left, I have the probability that the values of y occur that may occur when, that can occur when u lives in S, and may occur when it doesn't, and that's got to be at least equal to the probability mass this distribution of u puts on this set S. So these inequalities, you can kind of, I think, get an intuition that they must hold for every structure in the identified set. What you don't get an intuition on without going into some math and using some fairly new results is that this is a necessary and sufficient condition for this structure, for these structures to have generated the distributions that are used to calculate the probabilities on the left side. This is a characterization of the identified set. The proof uses results in random set theory. The main result is due to Zvi Artstein. Interestingly, given that he's a mathematician to the Hebrew University, actually a student of Aumann, who actually was one of the inventors of random set theory way back in the 1950s. It's rather a nice circle to see Artstein's material coming back into econometrics. Further results in Molchanov, and I should say Norberg as well. Tommy Norberg has some refinements that we've used. These methods we introduced into identification analysis by Berestiano, Molchanov, and Molinari. Our approach is different. We use the technology, but we work with random sets defined on the space of unobservables, because in our application, it's the unobservables distributions that are constrained by independence type restrictions, and so that makes sense to do that, and we get quite an economy by doing that. And these are moment inequalities or equalities. Moments, because these are probabilities on the left and the right. These are expected values of indicator functions, so they are expectations. And what we do in the papers is to characterize the required collection of sets. You don't have to look at all closed sets on the space of the unobservables. Actually, you only need to look at sets that are unions of the sets on the support of this, I'm going to say the word random set, which I promised I really wouldn't say, U. So that's what we need to do there. And we use results due to Galichon, Alfred Galichon, and Marc-Henri, and extend those results to refine the minimum. We try to get the smallest number of test sets, inequalities that are necessary to do the characterization of the identified set. What happens if the restriction, the independence restriction, is imposed? Right now, this is a completely vacuous statement. The left-hand probability is always greater than the right-hand probability, because the J set is a subset of the K set. So it isn't telling me anything at all. And you wouldn't expect it to. The econometrics can only proceed by putting some restriction on the distribution of the unobservables. If they can be dependent on Z in any way, we're going to get nothing. It's free lunch theorem. There is no such thing as it. So we have to put some restrictions on the dependence of U on Z. And the leading one is independence. Actually, in the paper, we look at mean independence and quantile independence as well, but it's no time to talk about that here. So I'm going to talk about full independence. Well, you can see if I say that U has to be independent of Z, only structures with that property are admissible, then in the middle, G of U given Z just becomes G of U, right? No dependence on Z anymore. And then there's a whole bunch of inequalities on the things on the left and the right that do depend upon Z. So it's going to be the infimum of the probabilities on the left has to exceed this, and the supremum of the probabilities on the right over all values of Z in the support of Z. So you can see where having good or bad support for instruments is going to be important in getting bite or not getting bite out of a particular data set, a particular model here. And woe betide you if the infimum of the probabilities on the left is less than the supremum of the probabilities on the right. What does that tell you? It tells you the identified set is empty. There is no structural function and distribution that can satisfy all these inequalities. And that tells you your model was misspecified. So it tells you whether or not, in some sense, whether or not this can happen, answers the question, is a model falsifiable? Whether or not it does happen tells you whether or not the model was a model delivering the process, delivering the data, was a model for which there is a process delivering the data that you saw. So we get this infimum and supremum result. And then a rather nice feature of this is that we can start to do semiparametric analysis. You know, when I did least squares, when I was taught about least squares, first of all, nobody said that like the error distribution had to be normal. Turned out I could identify the coefficient beta on y as beta x plus u without assuming anything about the distribution of U. And similarly here, I'd like to do that. And under independence, it's pretty straightforward to see what goes on here. The semiparametrics, look, if the structural function, all structural functions such that the infimum of the probabilities on the left is at least equal to the supremum of the probabilities on the right over the support of Z. If that holds, then I can always find a distribution of U to stick in the middle. Just take a convex combination of the left and the right and observe these probabilities all behave in monotonicity. As the sets get bigger, the probabilities get bigger. So this then defines the projection of the identified set onto the space of structural functions. If you like, it's a semi-parametric partial identification analysis, the power of an IV model. So let's apply this to this interval-censored endogenous variable problem. There, to remind you, here are what the U-sets are. They're closed intervals on the real line. Remember, beta is positive by restriction at this point. So beta y2u it's down below beta y2l, so it is a positive length interval here. And the collection of sets to be inspected comprises all intervals on the real line. So if we go through the business of figuring out, so what subsets of the space on which the unobservables live need to be inspected in order to get the identified set? What we find for this problem, and it's not a great finding, is that we have to look in principle at every connected interval on the real line. In practice, you can only look at a few hundred of those, and you have to be aware then that in practice you're always going to get some kind of somewhat outer region rather than the actual identified set. Now, if I'm going to go on, I need to figure out how much more time I have. You tell me, because I'm going to skip a bunch of... 10? Okay. Well, it's very difficult to make the decision now to do this, but let's try it, because a picture speaks 1,000 words, although sometimes this can be more confusing if you remember those quadrant diagrams you used to get in old times in economics, quadrant diagrams. There's one inequality for each interval on the real line. I did that. No, let me not do that. I'm sorry. Let me go back. Yeah, okay. So let's take a look. So there's the real line. I've left out quite a bit of it where the dots are, as you can see. And here's a particular interval that I might consider, a particular U set. And here's a particular test set. Here's a particular interval on the real line from T1 up to T2. And we ask the question, what values of y are such that this U set lies entirely within this interval, and it clearly really has to be values such that the magenta end lies above the value of T1 and the red end lies below the value of T2. So this is the inequality that's got to be satisfied. And remember now, what I need to do is calculate the probability this happens. I should have had capital Y's and Z's here, because these are now being thought of as random variables. So it's in this sense that we're dealing with random sets. These are random intervals whose position and endpoints are going to vary depending on the particular realizations we get of y of these various y's. And this probability just works out like this. And notice that since you will know the distribution of the y's given the z's, and since you could take any value of beta and gamma and actually calculate this object for any T1 and T2, it's something a computer can do for you. And if you don't know it, you can estimate it using data that gives you estimates of these distributions. So now let's look at the other probability. The values of y such that this set intersects with that set. If we go down, the set can go as far down as this, but the red part can't go outside the green part, and it can go as far up as this, but the magenta part can't go outside the green part. And so what you get is this inequality has to be satisfied, and we can work out this probability. Again, something you could calculate. It's probably easier to see when we put the final set of inequalities up. So these are the inequalities that have to be satisfied for every T1 and T2, or for every interval on the real line, and all betas and gammas that satisfy these inequalities will be in the identified set of values of beta and gamma. Notice in the middle here is the probability mass, the distribution if you puts on an interval. So that'll be the difference between the distribution function at T2 and T1 in this scalar case. And up here we have some inequalities. So the thing to notice here is that these two inequalities, they all look the same, but here it's y2l and y2u, here it's y2u and y2l. these guys are switched round. And that's what's important. And of course, this interval is much wider than this interval, but it may be that the inf of this probability over z is not much bigger than the sup of this probability over z. And indeed, if the model's misspecified, the inf will be less than the sup, and then you're all gone. I'm going to just illustrate what this set looks like. Probability is going to be generated by the sort of triangular model that people would actually often use in their empirical work, but who knows. With normality, Y2 star is going to be censored into fixed width non-stochastic bins, but I'm going to pretend I don't know about that, and I'm going to study the identifying power of this IV model. G0, G1, intercept slope. I'm going to presume to start with that use normally distributed with variance S squared. We calculate inequalities for some hundreds of sets on the real line. This is the three-dimensional set for G0, G1, and S. But it's interesting to look at projections, and this is actually particularly interesting, I think. So what we do here is we look at the inner set here. This is G0 horizontally in G1, intercept slope, the true values, as it were, in the data generating process, the red dot, 0 and 1. The inner set are the sets of values of beta and gamma that could have generated this data with a normal distribution for you, and a normal distribution for you, and the outer region is the semiparametric interval. It's also a projection against S as well, which shows you that normality actually buys you something in terms of getting a tighter set than not, but not as much as you might think. This is with a bin width of 0.4, and the coefficient on the instrument is 1, so it's quite a... here's what happens if I ramp up the coefficient on the instrument. So now the instrument is a much better predictor of Y2 star. And we see that the sets fall. And now I'm going to make the intervals have smaller width as well, and the strong instrument. And now you see the thing is getting really quite tight. And we do know, that if the instrument, what we know is if the bin width got 0, then this would be a point. That's one thing we do know. So there we are, there we have it. So new directions for IV. What we've shown in this work is that incomplete instrumental variable models, single equation, limited information models, can be used when outcomes are discrete or censored. I gave a talk recently at a conference for Richard Smith's 65th birthday on Tobit models. Tobit models with endogeneity, where we can do the same analysis. So since you can use IV models, it isn't necessary to use complete models. It isn't necessary to believe conditional independence restrictions in order to get information from data in this situation. But these IV models are with set-valued residuals are generically partially identifying, but we've characterized the sets they deliver, and we've illustrated the results. And notice that particular complete models that you might just decide to use, say with an equation filled in, if they're special cases of this IV model, must deliver points or sets within the sets that I've given you. So you can do this analysis and ask the question, well, does it really matter how I complete the model? If the identified sets are real small, it isn't going to matter. If the identified sets are real big, you better know that you're buying the precision that you claim to have, but through your belief in the particular way in which you complete the model. More on which in a minute, because I want to deliver a sermon by Koopmans, just to finish things off here. You can now start to implement these things. These sets are characterized by systems of moment equalities and inequalities. They're intersection bounds. We do have tools of inference available, and there are more papers that I should be referring to, but there's not enough time or space. These are the currently published papers. The most recent one here, Cherner, Zukov, Kim, Lee, and Rosen, is interesting because this is Stata code to implement this in particular problems. These are Stata do files. It's a paper on implementing this stuff in Stata. So this is within reach of applied researchers in simple problems at any rate. We've got our general results in this working paper in particular applications. There are other applications. And particularly interesting, actually, I think, is the paper I gave at the AEA meetings this January, in which we apply this to models of counterfactual processes. So we take the treatment effect type paradigm and apply this there, but with vectors of unobservables in each state, which you can never observe at the same time, and with a structural model that turns these unobservables into outcomes, but possibly incomplete models. You can get our papers here, but why bother with all this? Why bother? Look, there are perfectly good ways of getting point identification. As Whitney said to me, Andrew, you just have to find a control function. Perfectly good ways of doing this. Well, here's what makes me think. This is Koopmans and Reyersoll, 1950, Annals of Statistics in its old form, Annals of Mathematical Statistics. And so I'll preach just for a minute. Why on earth are we doing this for 10 years? Scientific honesty, Koopmans and Reyersoll say, demands that the specification of a model be based on prior knowledge of the phenomenon studied and possibly on criteria of simplicity, but not on the desire for identifiability of characteristics in which the researcher happens to be interested. I think it's time, as we say in England on the street, to man up and get to grips with partially identifying models. Thank you very much.
So we still have 1 or 2 minutes for quick questions. Any questions? I'm just curious, is the way we are doing the most efficient way to use that inequality set interval sensor?
Well, I haven't given you the theorems in all their precision. But these results these inequalities define the sharp identified set. Every structure that satisfies these inequalities can deliver the distribution that is used to calculate the probabilities that live in the inequalities. And that is, the reason why this is so is because what we use is characterizations of the property of selectionability in random set theory. So yeah, how you efficiently implement this with data is another matter, which I'll leave to much more clever people and definitely younger people and people with more stamina than me. Thank you.